Alright, this session we will spell out as clearly as I can the basic notion for the whole chapter. And there will be well over a dozen or more, 15 or so theorems based on this basic idea. And what is that idea? You take the computer type problems, like for example, does a particular machine accept a particular string? That's a computational type problem. And you translate that problem into a membership of a language type problem. And the two are equivalent. And that's what I'm now trying to show. Okay, so here's an example of a computational problem. You're given a DFA, call it B, and does it accept or reject an input string W? So you've got a random machine B and a random string W. Does this machine accept that string? And you're looking for an algorithm. Does it exist, yes or no? Does this algorithm exist which allows you to answer yes or no that this machine accepts this string? Random machine, random string. Okay? That's the problem. Okay, now take that problem and translate it into a membership of a language type problem. Okay, how to do that? Well, from well, you can't see it, but the previous, well, we'll do it here. Here's your ordered pair. It's a representation in string form, right? So you take the information about your B. That's all the necessary details you need to know what the DFA is. The DFA B, a particular kind of DFA, and all that information here is in B. And W is the string that you're talking about. And so you have this ordered pair represented in string format. That's what the angular brackets mean. And this ordered pair then, if you put that ordered pair, think of it just as an element, and you put it into a language, it becomes a member of a language. And call that language a suffix DFA from the previous session. Okay? So what does that mean? It means now the condition for this to be in the language capital A suffix DFA, the property that all the elements in that set, because remember a language is just a set of strings, in fact, and this is a string, right? Because of the angular brackets, it's a representation of the data of what the machine is and what the string is in string format, right? One-dimensional string of symbols. So this is a string. So that string will be a member of that language if, by definition, right? If this machine B accepts that string W. Okay? So if we can, so we're given an arbitrary B, just some arbitrary machine, and we're given some arbitrary string. Okay? We then form this string of these two, of this form, and then we go checking to see if this string here is a member of the language. Okay? And if it is, well, what can we deduce from that membership of the language? If this string here is a member of the language, well then, by definition, for that member to be in that language, by definition, it means that this accepts that. Right? So we have an answer to our question. Yes, the answer is yes, it does accept. This machine does accept that string, because this string here, we're talking about two different strings, right? That's your input string to the machine, and this is the string that is the representation, the encoding of 2 bits of information. Don't be confused, right? We're talking about two different strings. That's the input string to the machine, and this is the string that is a member of your language, a suffix DFA. Okay. All right. Okay. Well, suppose if it is a member, then you know this machine accepts that string. Now, say it's not a member. Well, then you know that this machine does not accept W, right? But so let me qualify that somewhat. We need to show that this language is decidable. Okay, what does that mean again? Again, just quick revision. A decidable language, what is that? That means there's some algorithm, some Turing machine that accepts every string in the alphabet and rejects any other string. Okay? So it makes a decision to accept or to reject every string that it comes across. It's a decider. Okay? And a language that consists of strings that are accepted by a Turing machine, and that all other strings are not accepted by that Turing machine, that algorithm, then such a language is decidable. The Turing machine decides the language. It accepts all the strings of the language and it rejects all other strings. That's what a deciding Turing machine, a decider, is. Okay. All right. Well, let's say there is such a Turing machine that does do that. That there is a decider for that language. Let's say it exists. Well, that means then that any string. Now, this is a string, right? That's a string. Now, if that string is not a member of the language, then the Turing machine, this algorithm, will reject. It will reject that string. Okay, because it's a decider. It's a deciding Turing machine. All right. So we can conclude, if we have this, if the language is decidable, in other words, if big A sub DFL, if that language is decidable, then there's a Turing machine that decides it, right? So if B does not accept W, if this DFA does not accept this, if this random machine does not accept this random string, then this string, the whole thing, this string here, is not a member of big A, the decidable language. Okay, you follow that logic? If not, rewind, play it back till you get it, because it's critical. We'll use this reasoning again and again, multiple times in this chapter. It's basic. Okay, well, I hope you follow that, right? So this is what I'm saying effectively. So showing the language is decidable. Okay. Now that's just the same thing as showing that the computational problem is decidable. Very important. So you can if the computational problem is decidable, that means it's you can make the Turing machine makes the decision on it. Is it yes or no? I mean, is the string accepted by the machine or is it rejected by the machine? That's what's meant by the Turing machine deciding. Okay? In other words, the Turing machine never loops. It's a decider. Right? It'll always terminate. It may take a long time, but it will always terminate.